Okay, so you can think of this as a virtual workshop. And in this workshop, I'm going to teach you how to solve some physics problems with some code. But don't worry, you don't need to know any programming beforehand. But let's just get started. So I will include this link down below. This is a link to all the material, most of the material in this presentation. And let's start with an example. So here we have some pictures. This is a picture from the movie Hidden Figures. Excellent movie. I highly recommend it. This is the movie, the Pixar Merida. What's the name? Well, she's like this girl that shoots a bow. I can't remember. It's a Pixar, and is it Pixar or Disney? I can't remember. But it's a great movie, even though I can't remember it. The one on the bottom. This is a weather simulation of weather calculation, and that's like, I think that's a storm. And over here, this is protein folding. So we have, in real life, there are these proteins, and they like fold over each other, and they make really weird things. But super important to understand how that happens. So what do all of these have in common? All of these are things that we can't do without a computer. Okay, so, well, we could, but we can't do these in the way that you normally would think of solving physics problems. Instead, we have to break these problems into small steps. So the Hidden Figures one is about which is a great movie. Really, you should go watch it. It's about using computers to solve problems to figure out how to fly in space and land. Okay, so we're going to use what's called numerical calculations. We need to do this in physics because it allows us to, one, understand problems at a different level, and two, do problems that you couldn't normally do. So some people call this computational science. Computational numerical is really the same thing. I like to call it numerical calculations. And I'm going to show you using Python. But you don't have to do it on just Python. Python just happens to be the programming language that I like the best, and I think it's the easiest, and it's the best anyway. But you could actually do this without a computer at all. You could do it on paper, and we're going to do that. You could use a spreadsheet. You could use Java. There's Scratch. It's this MIT graphical programming language. I think it's still around. There's C++. There's Mathematica. And I just want to mention also that there's Python, and then there's VPython, which is what we're going to use. VPython is actually Python with a module loaded, specifically made for physics and learning, and it's great. And there's a link right there to just how that came about. Okay, so if you've never made a program before, that is totally fine. Okay, do not expect, oh, I'm not a programmer. No, you're fine. And if you've programmed a lot before too, that's okay too. I'm going to assume there's no background. I'm also going to give you some problems, and I'm going to want you to pause to work on the problem. Okay, and that is important. If you just fly through this without pausing, it's not going to be the same thing. But I can't stop you because you're on your own, right? Okay, so here's the first problem. Here is a car on a track. At x equals 0, at time t equals 0, it's at x equals 0 meters. And it's moving with a constant velocity of 0.45 meters per second. So the question is, where will the cart be at t equals 1.5 seconds? Go ahead and work on this problem. If you want to work with a group, I'm cool with that. If you don't have a group with you, just do your best. You don't have to get it right. Just work on the problem. And take time, right? Don't just think, if I can't solve this in 5 seconds, I'm not going to do it. Take a good 5 minutes. That's fine. Okay. So pause this video, and then we'll resume. I was serious about pausing it. Pause the video. Okay. I assume that you did it. Okay. If you didn't, still pause the video. If you don't do this, you're not going to learn without doing. Trust me on that one. So here is how to get the answer that you already got, because you got it right. I know you got it right. We can start with the definition of average velocity. It's defined as the change in the x, and this is just in the x direction. The change in x divided by the change in time. Remember that little triangle is the Greek symbol delta, and it literally means change in. If I replace delta x with x2 minus x1, so this says the final position minus the initial position divided by the time interval delta t. I multiply both sides by delta t, add x1 to both sides, and I get x2 equals x1 plus v average delta t. Now I can just put in all my values. x1 is where it started at, x equals 0. V average is the velocity. It's constant, so it doesn't matter. 0.45 meters per second, and the time interval was 1.5 seconds. So if I put all that together, I get a final position x2 of 0.675 meters. Cool? Okay. Let's do the problem again. What if I do the same problem, but with a time interval of 0.25 seconds? So instead of 1.5 seconds, what if I do 0.25 seconds? So where would the car be after 0.25 seconds? And then I can say, okay, now I know where the car is, and I can go from another 0.25 second interval, and that can do it again. So instead of one calculation of 0 to 1.5 seconds, I'm going to do a whole bunch of 0.25 second calculations. Let's do that. So here is a table for you to fill in. And this table is going to help, and you really should fill in this table. It doesn't have to be perfect. You can just write it down on your paper, okay? You already have paper out because you did that first problem, remember? So we're going to start at time t equals 0, and the time step is 0.25, and x at that time is 0. So I can calculate the next time in the next row right down here by just taking this time, t1, plus the time step, dt, and I get t2. That's not hard. I can calculate the next, and the dt's are all the same. I shouldn't even put a column there. The x2, I could do the same thing. I could just do x1, which is 0, plus the average velocity of 0.45 meters per second, times a dt of 0.25, and I could get that velocity right there. If you did that for the first column, you get this. So I get 0 plus 0.25 is 0.25. That's still the same. This is 0 plus 0.45 times 0.25, and I get 0.1125. So after 0.25 seconds, this is where it's at. So see, and now the next time right here, I'll go ahead and tell you, is 0.5 and then 0.75. So you can fill out all these times. We want to get all the way down to 1.5 seconds, and we want to find out what the position is after 1.5 seconds. Now, quick note, to find the next position right here, I'm going to take the position before, right here, 0.11, times the velocity of 0.45, no wait, plus 0.45 times 0.25. So always start with the position before. Don't always start back from the beginning. Okay. Okay, so pause the video. I really, really mean it. And fill out this table. And I am going to have a sip of coffee while you do that. And then I'll show you the answers. But you need to do it. Go. Okay, please tell me you paused the video and filled out the whole thing. It's important that you do. I'm going to show you the answer, but it will be useless if you did not first fill out the. If you filled it out and did it wrong, that's good. If you didn't fill it at all, then I don't even know what you're doing. You might as well watch this whole video in double speed and just get over with it. Okay, so here are the values that I get. The times all increase by 0.25. Each of these delta x's is calculated by the one before it. And then down at the end, I get a final position of 0.675 and a time of 1.5. That's the same thing as before. And you may think, this is silly. We already calculated that. You're wasting my time. I could be doing something else. True. But we're going to get to a part where it's not wasting your time. It's practicing stuff that we can do two ways so that we know really how to do it. Okay, the next step. Oh, this is the important part. You are a computer. Literally, you computed the position of that object in multiple times. You broke the problem into small pieces. That is exactly what a computer does. And in fact, when you say computer, most people think of an electronic computer, but the original people were just people. The original computers were people. So in the movie Hidden Figures, I like to go back to that movie because it's so great. The females that were calculating stuff for NASA were computers. Okay. When at the end of the movie, spoiler alert, but it's a real story, so it's not a big deal. They have an electronic computer that they're transitioning to, and so but the original term computer meant a person that calculated these things. So that's what it is. So how do we make this into a numerical model? We have this equation. I started off as x2 equals x1 plus v average delta t. But this is also could be used for any successive x positions. Here's an example of x7. The 7th x position is equal to the 6th x position plus average velocity times delta t. And we're going to call this the position update formula. So if I know my velocity and I know my current position, I can find the next position based on the time interval. And we're going to use that a lot. Okay, let's do this in Python. We're going to do the exact same calculation in Python. I'm going to step you through it, so don't worry. This is where if you go to the website that I have here, it's linked down below, and you click on a car moving with a constant velocity, you have the same problem there. Everything that I've said is in that thing too, okay? So if you don't want to listen to my voice, you could just read it, and that'd be cool. But that's where we are. So let me show you what this program looks like. This is Python, okay? So, and this is actually Python in Trinket.io. So Trinket.io is a really nice place in that it has Python in a web page. So you don't have to install anything, even though Python is free. And it runs in a web page. It runs on your phone. It runs on your tablet. It runs pretty much everywhere. So on the left side here, you have your code. On the right side, you have your output. You push this little play button right there to start the program. If you ever get stuck, you can always click these bars right here and reset the code. So that's really nice. So let's just go over some points in this program. So the first thing is there's numbers that I start with. These are my initial conditions. You have to numerical calculations depend on numbers. I have to have numbers in order to do the whole thing. So I need to know where it started, what time it was, the velocity, and the time step. And here I picked 0.1 seconds instead of 0.2, but we can change that. This code in Trinket, you can change this and rerun it, okay? And you should. Now the next thing is line 6. This is a way to tell the computer how to do all of the calculations. Instead of writing out all the calculations manually, I just wrote this. Line 6, 7, and 8 is actually a loop. So this says tells the computer do line 6 through 8 until t is no longer less than 1.5. So when it stops, t will be equal to 1.5. Okay. Now line 7 is very confusing looking because this says x equals x plus v times dt, and there is no numbers. It's not x2 equals x1. And don't you think x's should cancel right here? And this is because this is not an algebraic equation. This is a make equal to equation. This tells Python, take the velocity, multiply by dt, add that to the position, and then make that the new position. So I don't have to have, 100 different variables for x. I just have one and I keep updating it. And the same is true for time. Now, the other thing for a loop in Python, we have this colon right here to start the loop, and everything that's indented, tab indented, is in that loop. Once I undent, I'm no longer in that loop. So this print statement down here prints out the final position. And you see my output over here, I get 0.675. So I get the same thing. But there's no units, okay? Your physics professor is going to say you got to have units, and that's true. But this is a computer. They're not that smart, right? If you put a 0m, it's going to not know how to deal with that. It has to be a number, okay? The units are your responsibility. Okay. Oh, and if this is, if you just have one window on your phone, this will be a pencil right here, so you can switch between edit and play. I think I already talked about this. Oh, you do have to have the asterisk for multiplication. If you put VDT, then Python's going to think you have a new variable called VDT. Okay, so go back and open up that program. You're going to have to pause the code, the video here. Run that program and see if you can edit the program and find out where the car will be at 2.2 seconds, not 1.5 seconds. Okay. Answer the next question. What if the cart has a velocity of 0.62 meters per second? Where will it be at 2.2 seconds? And then what if the cart starts at x equals negative 0.5 meters and has a velocity of 0.62? Where will it be at 2.2 seconds? Okay. So go ahead and do those. Pause the video. Really, I'm not even going to give you the answers, okay? Because so you can pause and or not pause. It doesn't matter to me. I will. If you have a problem, you contact me later. We'll talk about it. So you should pause. Okay, unpause. So the key here, though, is if you change that code in any way, you've now transitioned from not being a computer programmer to being a computer programmer. So it wasn't that hard, okay? So I don't want you to have that fear of, oh, I can't be a computer programmer. Okay, let's do another example. Here's another question. You can solve this on paper. It's the same cart, x equals 0 at t equals 0, has a velocity of 0.45 meters per second, but now it is also accelerating at 0.2 meters per second squared. What's the position after 1.5 seconds? Go ahead and solve that. Pause this, really, really pause it, and really work on it. Okay, here is, I know you got it right, so I'm going to just to verify that you got it right. So here we're going to start with the average velocity, and now we have also the acceleration. It's the change in velocity or the change in time, because the velocity is not constant. We also have this definition for average velocity where I just add the velocities and divide by 2. If I mix all these together, and I've skipped over the derivations, I actually have talked about them before, you get the following kinematic equation. This says the final position is equal to the initial position plus the initial velocity times the time interval plus 1/2 a delta t squared. And if you put in your values at 1.5 seconds, you get 0.9 meters. And you'll notice that it is farther than the previous example because it was increasing in speed, so that makes sense. Okay. So again, what if I break this into small steps like I did before? I can still use the position update formula, but now I also have to change the velocity because the velocity is not constant. So if I take this equation, a equals v2 minus v1 over delta t, and solve for v2, I get this equation, v2 equals v1 plus a delta t. It looks just like the position update, but for velocity. Okay. Now, here is a trick. So this is no longer, this is true, this v2 equals v1 plus a delta t. It's exactly true. But this equation, x2 equals x1 plus v2 delta t, is wrong. It should be the average velocity. And here is the magic of numerical calculations. If delta t is super small, then this is only kind of wrong. And kind of wrong is kind of right. Okay, so we're going to do it anyway and no one can stop us. And here is how we're going to do that. So here's the same table that I had before, except I've added a column for v right there. And we're going to calculate manually by hand and fill in the rest of this table. So we're going to calculate the time. We're starting with 0. We're starting with the velocity of 0.45. We're starting with position 0. And then I'm going to calculate dt the next time by taking this time plus that. All the dt's are 0.25. To calculate the next velocity, I'm going to take this velocity times the plus the acceleration 0.2 times dt. I have that right down here, v2. And then to find this next position, I'm going to take the previous position plus this velocity, which I just calculated, not the one before it, times dt. Okay, so if I do that for my first row, I get that time. That's the same. This is not the average velocity, but it's close, right? You could actually average those two. And this is the position which is wrong. Technically wrong, but only kind of wrong. So pause this video and see if you can fill out the whole thing. I think that you can. It is, you may say, okay, it's repetitive and boring. That's kind of the point. Do it, okay? Pause. Okay. Hopefully you filled it out. Even if you got it wrong, that's cool. But here I get all my t's are easy to do. My velocities, these are all correct. This is not correct. right? Remember, we said the final answer we calculated exactly was 0.9. Here I have 0.9375. So it's not quite right. That's fine. Okay. Because we cheated, right? We cheated by breaking. We made this thing that wasn't true. We said V2 instead of V average, and that's not true. Okay, let's do this in a Python code. And so you'll notice there's only 2 lines that are different. 3 lines. 2 lines that are different from the previous example. The first line that's different is this. Line 4, a equals 0.2. You can make up any variable you want in Python. Well, there's some words that are reserved, but it does matter for the case. I will say that. So here I just made up a variable called a. It doesn't actually have to be a. You could write out acceleration if you wanted to. And I put it at 0.2. I changed the time step to 0.1. The another step here is on line 8, I update the velocity. And it actually is important that you do this before you update the position. So just letting you know, do that. If you change the order there, you can play around with that. It's kind of fun. And I print out the x. If I do that, this is a time step of 0.1. I get 0.915, which is closer to 0.9, but not the same. Okay, but it's not bad. It's really not bad. Okay, so here's what I want you to do. This code is in that page, that trinket page. You can go down there and edit it. And these questions are even in that page. So answer the following questions, which I'm not going to answer for you. I'm not going to tell you the answer. What happens if you change the final? What happens to the final answer if you change the step size to 0.01 seconds instead of 0.1 seconds? So here you can see you don't want to do a table where the time step is 0.01 seconds. You'd have 150 rows in it. No one wants to do that, right? What if I change the acceleration to negative 0.01 meters per second? Where will the object end up? And then this last question is tough. Okay, it's tricky. I will admit it's tricky. If you don't get this one, I'm fine with that. We can talk about it later. If the acceleration is negative 0.02 meters per second, how long would it take to stop and where would it be? So I said print the velocity at the end of the loop. If you go down here, you can print whatever you want. You can put whatever variable you want there. You can print v and just run it and see if it did stop. Okay, you could actually put another statement down here, print x, print t. You could print as much as you want. And I'll show you how to print better in just a second. Okay, so pause and work on those questions. Edit the code. I want you to break the code and do something such that things don't work at all, because that means that you're really trying to do stuff, and I'd be proud of you. So do that. So pause it, and then I'll show you how to get better print statements. Okay, here we go. Here is some better stuff, some better print statements. So first, I want to point out comments. So we can add comments to our code because humans read these. You're a human, I'm a human, and the computer doesn't care. It ignores these comments. But if you put in a number sign, or as some people like to call it, a hashtag, then anything after that is just a comment and the computer ignores it. One of the things we can do is to put things in here to remind ourselves how things work. We could also use it for units. If I put in line 5, x equals 0, number sign m, it says, okay, I know the unit for x is meters because that's what I'm recording it at, just for my own knowledge there. I could put in comments like this, update the velocity, update the position, so I know what I'm doing. The next thing I want to show you is the print statement. So the print statement, instead of just printing a variable, I can actually print a line like this. The car is at x equals, comma, and then a variable, and then I can print some more stuff. And so you can get the output that looks like this. I can get a whole bunch of better stuff. Now, there is one other thing that you can do that will really help, and I didn't quite finish because I'm going to pause this video. I'm going to end this video and start another video, and that's what if I want to make a graph of the motion. That is very useful too, and you really need to do that. So I'll wait because you need a little break. Take a break, answer the questions, make some cool print statements, do those 2 things, and then I'll start part 2, and I'll show you how to do graphing and deal with other things with motion, and I will talk to you guys later.